Okay, so today I'm going to present some joint work with Stefan Wenger, who's at University of Illinois Chicago. And we posted one of our preprints, and we have another one coming up. So what we've done is we've defined a new distance between oriented Riemannian manifolds and called the intrinsic flat distance because it's based upon the flat distance of Federer-Fleming. We use the notions, Ambrosio-Kirchheim has extended the flat distance between integral currents to metric spaces in general. And limits of sequences of manifolds with respect to our intrinsic flat distance are countably rectifiable metric spaces, so they have these Lipschitz charts all over them. And they have orientation, they might have multiplicity. And in general, the Gromov Hausdorff and the intrinsic flat limits are not going to agree, and so we analyze situations in which they do agree. In general, our convergence occurs for larger class of sequences. So there are many sequences that don't converge with Gromov Hausdorff since they do converge now. And we do show that in the case of non-negative Ricci curvature that the two limits do agree, and also when there's uniform linear local geometric contractibility functions. So I'll define all these things during the talk. So let me just give a brief history about the convergence of Riemannian manifolds. There was C1 alpha convergence, where you have to compare diffeomorphic manifolds, and you map the one metric over to the other, and you look at the C1 alpha convergence of the metrics. There's a compactness theorem there with Cheeger, which assumes sectional curvature bounded on two sides, the volume bounded below, and the diameter bounded above. So sequences that have these bounds have subsequences that converge. Anderson has a compactness theorem where you assume only the Ricci curvature is bounded on two sides, and in place of the volume bound is an injectivity radius bound. Cheeger's compactness implied the injectivity bound as a consequence of this condition. Gromov Hausdorff convergence leaves out the necessity of having an injectivity radius bound, but the limits are no longer smooth manifolds. They're just compact geodesic metric spaces. The topology can change in the limit, the dimension can change in the limit. There's a very nice compactness theorem where you assume only a Ricci lower bound and a diameter bounded above. And the intrinsic flat convergence, the limits are no longer necessarily compact geodesic metric spaces, but they're weighted, oriented, countably rectifiable spaces. So they have more smoothness than the Gromov Hausdorff limits. And my co-author has a compactness theorem where all you need to assume is a diameter bounded above and a volume bounded above. So it's a very large class that has this convergence. Another interesting thing about our limits is that the dimension is the same in the limit as the sequence.
Is it a metric space?
It is a metric space with Lipschitz charts. So let me give a little bit of background. The Hausdorff distance, defined by Hausdorff, you take two subsets in a common metric space Z, and you define the distance between them by taking a blurring of the one and seeing if it overlaps the other, and then you blur the other and see if it overlaps the first. So you take two real neighborhoods and you check if they contain each other. And the smallest radius that works to have them contain each other is the Hausdorff distance. Gromov's Hausdorff distance is an intrinsic version of the Hausdorff distance, and the way he makes it intrinsic is he takes an infimum of the Hausdorff distance between two metric spaces. I take the two metric spaces, they don't exist in the same place, so you have to put them into a common place. So he takes isometric embeddings, puts them into a common metric space, checks the Hausdorff distance, then tries it again, lines them up, and then takes the infimum over all possible isometric embeddings and all possible metric spaces. And this Gromov Hausdorff distance has a blurring effect, so a sequence of tori getting thinner and thinner converge to just a circle. You see the dimensions dropped here, and also the topology has changed. So Gromov's compactness theorem is actually much more general than having a Ricci bound. You could just have a sequence of metric spaces with the diameter bounded above and a uniform bound on the number of balls that fit in the space that are disjoint. So it's like having an equicompactness condition. When you have compact space, you can count the number of balls, and in this case, you can count the number of balls uniformly for all the xj's. And if you have this, then a subsequence converges in the Gromov Hausdorff sense.
For all R.
Yeah, you have to have it for enough R. And then you end up having it for all R. Yeah, but then it ends up being true for all. The converse also holds, that's why it ends up being true for all, which is that if you have a sequence of converges in the Gromov Hausdorff sense, then a uniform upper bound on diameter results. Here we're going to assume the limit space is compact. And you have a uniform number on the balls in the xj's. So here's a sample of a sequence that was disturbing to some people that doesn't have a Gromov Hausdorff limit but has a natural expected limit. If you take a sphere and you put a metric on it that has bumps, so you see the blue tips here. If you put a ball centered at the tip, on each tip, you'll see that the number of balls increases for the sequence. So this is not going to converge in the Gromov Hausdorff sense. However, one should sort of expect that this sequence ought to converge to a sphere if these tips are small enough. That there's sort of an intuitive feeling that this ought to converge. And this would be nice, for example.
The spikes are not getting shorter, right?
Spikes are not getting shorter, they're just getting denser. So the computer made this effect where it's just looking blurrier and bluer. Lehman suggested that he felt this ought to converge to a sphere, this particular sequence, because he felt that it was natural that these gravity wells would sort of not be seen in the limit. But there wasn't any convergence that would allow for this. So he had suggested perhaps one could define a weaker convergence, a Gromov Hausdorff convergence, where this sequence, if you assume positive scalar curvature, for example, would converge with 3 spheres. So this would be a sequence of 3 manifolds, as opposed to, I drew it like it's 2 spheres, but his suggestion was 3. Okay, the reason that Gromov's compactness theorem applies to Ricci curvature is because of the Bishop-Gromov volume comparison. This allows you to compare the volumes of small balls, that they're larger than certain ratios times larger balls, so this allows people to count the number of balls inside a space with the Ricci boundary below. And so they always have a subsequence that converges in the Gromov Hausdorff sense. Cheeger-Colding proved the non-collapsing theorem that if your sequence has a volume boundary below, so not like those tori, the tori that got thinner and went to a circle, the volume is not bounded below there. So they said, well, if you also assume the volume is bounded below, they proved that the limit spaces have the same dimension as the sequence. They're countably rectifiable, and actually even a little more. So there's all this Lipschitz charts all over the place on these limit spaces, which doesn't come at all from Gromov's work. In fact, it uses a Brush-Gromoll's theorem, their proof. They show a certain amount of splitting inside the limit space. And so the limit spaces have these Lipschitz charts onto them, which is the same dimension as the sequence. And this is intriguing because ordinarily the Gromov Hausdorff limit could go up or down in dimension, and that there is never any notion of rectifiability coming from Gromov Hausdorff convergence. They actually add a measure, they keep track of the measure, and do a lot of work to get this result. So if one tries to find a new kind of convergence, can it have a compactness theorem that's usable in the setting with positive scalar curvature? Can we make this sequence converge? And can we explain why the limits with the non-negative Ricci curvature are countably rectifiable in a different sense? Like, is there a geometric reason for it? Instead of all the effort that Cheeger-Colding had to go into to analyze very specifically using the Ricci curvature. And the natural notion that comes up is flat convergence, which is a notion from geometric measure theory, where you have surfaces approaching minimal surfaces, and the limits are countably rectifiable. Sequences like this converge, and so that it's much weaker convergence than Hausdorff convergence. So it fits these criteria. The question is, how can you make an intrinsic version? So let's go over the flat convergence. Federer-Fleming came up with the notion of an integral current. So what you do is you take a submanifold of Euclidean space, so we'll just stay in Euclidean space for a little while. You take a k-dimensional submanifold of Euclidean space, and you think of this k-dimensional manifold as acting on k-forms. So k-differentiable forms sitting in the space, and you think of this submanifold as an integration over k-forms. So it's a functional on the k-form. Then, well, once it's something acting on k-forms, there's a notion of weak convergence. So a sequence of integrals converges to an integral if, whenever you test it on a differentiable k-form, it converges. That's a weak convergence. So they had this notion of weak convergence as integral current. So an integral current is defined by integration, and it can have multiplicities that are integers. It has finite mass, which means that the integration, it's like the volume, including the multiplicity, is finite. And they could also require that the boundaries, if there are boundaries, have finite mass for these integral currents. And this was used to study Plateau's problem and other problems in which one was concerned with infimum of area. So this picture actually comes up in that setting, or it fits that setting. Suppose you're taking a sequence of surfaces which are, the area is decreasing and the volume inside is bounded below uniformly. So you're trying to find a sequence that goes down to the smallest possible area for a filling volume. And as you progress, there's no reason why, even as the area decreases, that you wouldn't have spikes and all sorts of weird things popping up. So because of that notion that when you take a sequence of surfaces whose areas are decreasing, you could have all sorts of spikes. Actually, there's a really beautiful picture in this book of how terrible these things can look. Surfaces decreasing down. This is Morgan's book, and I highly recommend it. And yet you want it to converge to the surface with minimum possible area for the enclosed volume. And it does in this weak sense that I've just described. And so it was used in minimal surface theory and also in other PDEs all the time it uses. So the limits are not always nice smooth manifolds, but they are integral currents. So they are a notion of integration over k-dimensional countably rectifiable subsets. So there's all these Lipschitz charts in space. There's only Lipschitz. Now Federer-Fleming, this is repeat. So this is repeat of the definition of the weak convergence. So then what's the flat distance? Because you can't really, a weak convergence is hard to make intrinsic. It's hard to say, okay, this is notion of weak convergence, and now how do I make it intrinsic? It's easier to make something intrinsic if you have a distance. So Gromov has the intrinsic Hausdorff distance. He takes his manifolds and he moves them somewhere, and he studies the distance between them. So we needed a distance, and Federer-Fleming had a distance called the flat distance. And the flat distance agrees with weak convergence. Flat convergence and weak convergence agree when there's a uniform bound on the mass of a sequence and on the mass of the boundaries. That's called the total mass. So it agrees, so it's going to work well with the weak. So we can say that last sequence converges in the flat sense in Euclidean space. So the key concept you need to understand the flat distance is the notion of the mass of the current and the boundary of the current. So you think of the mass as just like the volume, counted with multiplicity. And you think of the boundary just as, if it's a submanifold, the boundary is just the boundary. You have a surface, the boundary is just the boundary of the surface. But the boundary in general is defined, remember it's an integral. The boundary is defined using substitute. Okay, so the boundary of an integral is the integral acting on D of the form.
If you multiply it by a half, you're not allowed to do that, right?
Not allowed to. We're sticking to integer multiplicities for this. So Federer-Fleming study in the broader class. So that integral ones, integral currents stick to integer multiplicities. There's other currents. So Ambrosio-Kirchheim extended the notion of the integral current. So it doesn't have to be in Euclidean space anymore. Now you could have your integral current sitting in any metric space. This is really profound deep work because we had defined integral currents using differential forms. So they don't have any differential forms in their metric space. So they had to come up with a notion to extend the concept of differential form, and what they used was m tuples of Lipschitz functions. So instead of an f dx1, which dx2, dxn, they use f, comma, x1, comma, x2, comma, xn. And then they made it act on that in a way that behaved just like the integral currents acted on force. And they used work of De Giorgi, who had developed that trick.
If you have a manifold, are the two notions the same?
They agree, yes.
That's not obvious.
It's not obvious. And Ambrosio-Kirchheim proved it, but not De Giorgi.
What?
Ambrosio-Kirchheim proved it's the same, but not De Giorgi. De Giorgi had extended the notion, but he didn't prove the degree. And then my co-author Wenger he's a geometric measure theorist, extended the notion of the flat distance to this setting. So, it follows, but then he also extended the fact that the weak convergence and the flat convergence agree, which needed a few extra conditions on the metrics to see, which we have. So, let me go over the flat distance. So you have a flat distance between two integral currents. So my first integral current I drew in red, and I made them one-dimensional for the picture. So the red integral current is just a straight line on the bottom, and the blue integral current T is something at the bottom. And I want to say, what's the flat distance between them? These things are not close in the Hausdorff sense, because if I take a tubular neighborhood about the red one, it doesn't really include the blue one until it gets really large. But they are close in the flat sense, because the flat distance asks you to find the smallest possible sum of masses such that you can attach them on the ends to the little green pieces. So that's our A. And then fill in. So you attach it so it's a cycle. You create a cycle. So S minus T minus A is a cycle, and then you fill it in with B. So B is the yellow part. And you want to take the smallest possible mass of the A plus the mass of the B. Now this is just a one-dimensional picture. You'll notice the B is always one dimension higher because it's a filling. So the B is like a filling, and the A is like, let's close it up so we can make a filling. And you do this. Now, I could have made A very long, and then B would be too large in this setting. Or I could make A come in more if I wanted to make B smaller. You take the infimum over all possibilities, and that's your flat distance. And a co-author has proven that this infimum is actually achieved by a pair of integral currents. It's achieved. So it's not just an infimum, it's actually a minimum. And that's handy. That was also known to Federer Fleming in the Euclidean space. Okay, so now I have the flat distance. So here's I restate the distance, so it's handy. And let's look at this sequence. If you think of these spheres as all being right on top of each other with bumps coming out of them, and you take a sequence, then the A, right, the A is something is not even necessary in this case because there's no need to fill in between. And you can just fill them with just the B. So the B would be the space between the sphere and the bumps. So as long as the volume of the bumps, inside the bumps, gets small, we're fine. This actually gets close to zero. So those bumps were getting very, very thin, even though they stayed the same height. If you had assumed the area was decreasing, for example, then this would definitely be converging.
And what response of converging to the sphere, the bigger sphere, which is sort of circumscribing the tips of the bumps?
Yeah, well, the only thing to stop it is that in this picture here, the bumps are drawn narrower than the spaces between them.
Ah, gotcha. And you wouldn't get, and if you tried to split the difference, you wouldn't get convergence to either.
Then the area would be going to infinity. Yeah. So to make an intrinsic notion, we cannot allow the dependence on the embedding of the manifolds. Okay? So right now this is still just a flat distance sitting in a given metric space. And we want to make an intrinsic notion so we can compare two Riemannian manifolds that are not sitting in the same place. We compare Riemannian manifolds to each other. So you have one Riemannian manifold, another Riemannian manifold. We're going to use Gromov's idea. You take the two Riemannian manifolds, you isometrically embed them into a common space, check their flat distance. Do this again and again. Check all possible flat distances, all possible z's, and we will get our intrinsic flat distance. So the intrinsic flat distance is an infimum over all possible isometric embeddings, d and psi, and we take the manifolds and we put them into this place. So there's an interesting thing here. We're talking about a flat distance between integral currents, right? An integral current is an integration. So there's a notation from geometric measure theory that you put the sharp on. So I have to explain that a little bit. M is a Riemannian manifold. There's a natural notion of integrating over a Riemannian manifold. You can integrate. If it's a k-dimensional Riemannian manifold, you can integrate over k forms. You use the devolve, okay? So we have a notion of integration over a Riemannian manifold. Now we've isometrically embedded into Z. How do we integrate? We push forward. That's what the phi is sharp is. It's pushing forward this notion of integration. It says take your test current over there, take your test differential form over there, or tuple, pull it back to the manifold, integrate it. That's what that means. So you can think of this as we put M and N into the same space, and then treat them as integration over there. Or you can think of it as pulling back and integrating over here. Either way, it's sort of both going on at once. So you take them, you push them to the same place with an isometric embedding. And let me just emphasize what I mean by an isometric embedding. As in the Gromov Hausdorff case, we say something's an isometric embedding if it's globally an isometry. So every pair of points x1, x2 pushes to the same distance as they were before. It's not an action on the tangent bundle. Sometimes in Riemannian geometry, say isometric embedding, you just mean d phi is an isometry. We mean a global isometry. This does not work if you use local isometries. Everything is zero distance apart, unless you use global isometry. So we have a theorem that if M and N are compact Riemannian manifolds, and we need an orientation because we need integration, so it has to be oriented Riemannian manifold, then the flat distance between M and N is zero if and only if there's an orientation preserving isometry between M and N. So a Riemannian manifold and its opposite orientation are different things and have a distance between them. So this is an oriented notion. So we will say not orientable, but oriented Riemannian manifolds are arrow spaces. A manifold with this orientation. Okay, so now I put the two definitions up near each other, the intrinsic flat and the Gromov Hausdorff, and I'm going to keep these definitions up for future transparencies and show some examples. So this first example is just one bump. So you have a sphere with one bump on it, and the bump is getting thinner and thinner. And according to the Gromov Hausdorff convergence, you use tubular neighborhoods, and some people say it's a notion where you're blurring, that's what Cheeger likes to call it, that it's really looking at it without the glasses on. So you have the sequence here, and the Gromov Hausdorff limit is the sphere with the line segment on it. The flat limit doesn't see that bump because the filling gets smaller and smaller. So the flat limit is just the sphere. Let's get that one. For this one, there's no Gromov Hausdorff limit, but the flat limit, again, we fill it in. And the filling actually has to be done cleverly. I can't just sit this in Euclidean space and fill it, because that would not be an isometric embedding. I have to think of this as a Riemannian manifold with bumps. When I fill it in, I have to do it really carefully and fill it in some isometrically embedded metric space Z. So we did that, and then we get it to converge in the intrinsic flat sense to a sphere. So what about this example? It's Cauchy with respect to the intrinsic flat distance, but the limit is not a Riemannian manifold. This limit is a pair of spheres. The metric on the spheres, it's a metric space. But the metric on the spheres is as if there was a line segment between them. We don't see the line segment. So we have to extend our notion of what our spaces are. Here's another sequence. If I take spheres and join them with tubes, and I take more spheres and join them with more tubes, the limit in the Gromov Hausdorff sense would be a huge collection of spheres joined by line segments. And the intrinsic flat limit will be just the spheres with no line segments. And that space, you see, has so many different but countable collection of spheres in it. And that's crucial that it's a countable collection. So in fact, our limit spaces in our intrinsic flat sense are always going to be countable collections of things that are the right dimension, while the Gromov Hausdorff limit can go up a dimension. If I had made this denser, the Gromov Hausdorff limit would be higher dimensional. But our limit won't be.
Space are not compact. Your limit.
That my space may not be compact, that's right. It will be pre-compact. So our limits we have to define, and we call them integral current spaces, because it's natural, they come from integral currents, so we call them integral current spaces. So integral current spaces, this countableness that you saw in that picture with all the spheres, they're countably HK rectifiable. That's a notion that's been well known and studied by Kirchheim a lot. And basically what it means is that you have charts. The charts are Lipschitz. You can make them by Lipschitz if you want, from Borel sets inside Euclidean space to the space. And you usually don't make them overlap. So they're disjoint charts. And they're all the correct dimension, the k dimension. And then you say that they cover almost all of the set. So they may not quite cover everything, but they cover, in the correct Hausdorff measure of dimension k, they cover almost everything. So we've got charts, and it allows us to do all sorts of things like the coarea formula. You can, there's a notion of a tangent plane in this world of rectifiable spaces. There's a lot of notions that already exist and have been proven for this kind of space. They can be chosen to be by Lipschitz and disjoint, are charts. And there's an orientation. That's a preferred collection of charts, just like orientation we're finding about.
What's the coherence?
No coherence. I can make it plus minus plus minus. But once I define it, it's there.
With uncountable many orientations.
Countable.
Uncountable.
Oh, okay, okay. Given a chart, once you've set your chart, yes, there's uncountably many possible orientations, I agree. But our spaces will be oriented and countable, just like our Riemannian manifolds will be oriented. We already have an orientation on our spaces, and our limits will have an orientation forced on them. Multiplicity is a Borel measurable function whose values are integer. I didn't, for some reason, left out integer. So in all, we can put it together. It's a metric space X with a metric D, and T is what we call the current structure. This current structure T captures this multiplicity and orientation. So T is actually a K integral current on our K-dimensional space. Just like the volume is a current on a Riemannian manifold. So it's a correct dimension, and we set it up so that this thing called the set of T equals X. The set, or canonical set, of an integral current is defined by Ambrosio-Kirchheim. And I'm going to describe it a little more. The idea, though, is that we have the same dimension between the integral current and the space. And by defining it this way, it matches the Riemannian notions better. So here's a little more about the set. What does it mean to say that our metric space X is the set of the current? It means that the mass, or the volume, that the mass is measured with the current, divided by the correct dimension R of the K, that this is positive density. So our limit, so these masses, so that formula might bother some people, so here I'm just drawing some pictures. So in the pictures, what it means is, if you have a conical singularity, you include it. Conical singularities are included in the set, and so they're included in our space. But a cusp singularity, where it comes in like a cusp, we take out the singularity. It's not included in our space. So the canonical set, which is defined by Ambrosio-Kirchheim, of a current does not include any cusp points. It only includes points to which positive density, so that the mass, just like in a Riemannian manifold, the volume, as you approach a point, behaves like R to the correct dimension. The idea is to do the same effect. You need that in order to have this nice charting effect with the Lipschitz charts. So we don't include these points, and so our spaces end up being pre-compact, because we're not including any of those cuspy points. Although they can be achieved, you see. This sequence of Riemannian manifolds is converging in the Gromov Hausdorff sense to a sphere with a cusp, and in our sense, we don't include the cusp. Now that looks trivial there, but it becomes very important later. Another interesting aspect is that our spaces include zero space. The zero space occurs you a picture a little bit later. There's a possibility of the zero space being our space. So once we have our spaces, the x, dt, the intrinsic flat distance between two spaces can be defined in general. Like we just take all isometric embeddings of the x's of the metric spaces into a common space, and then we measure the flat distance between the push forward of the current structures. So the Riemannian manifolds, you push forward with the Riemannian integration. Now we take any pair of metric spaces and push forward their current structures. So we have a notion of distance there, and we can show that the flat distance between two of these integral current spaces is zero if and only if there's a current preserving isometry. So before it was orientation preserving, now it's current preserving. So we have a map which takes orientation to orientation, multiplicity to multiplicity. That's all that really means. Okay, so we can take oriented regions, go to this oriented the same way, and if there's multiplicity 2 here, it goes to multiplicity 2 there. It's crucial in the proof of this theorem that we use the set. In this picture, if we didn't use the set, okay, so this picture is not quite as bad as what one could draw. I could actually draw, oh, I can't with the computer. In your heads, you can draw spheres that become dense. And even though the total area is still finite, you could draw in a cube spheres that are dense with total area finite. That is a possible limit. The Gromov Hausdorff limit of something like that is the whole solid cube. It went up a dimension. But our integral current keeps track of that as only those spheres. So we're not taking any points that are just limits of spheres. We're only including the points in the set, the positive density points. So we actually still see all those countable spheres in our limits. And we still have the Lipschitz charts that are the right dimension. So even though your limit space could be quite horrific and quite overlapped looking, but actually not overlapped, the Gromov Hausdorff limit could be higher dimensional. Our flat limit will be possibly a dense subset with the correct dimension. So we're very careful not to take closures. If you take closure, your dimension can jump on. Okay, so let's have some theorems. So one of our first theorems is that if you have a sequence of oriented Riemannian manifolds, so let's go back to Riemannian, and the volume is bounded above, and the volume of the boundaries are bounded above, and the sequence converges in the Gromov Hausdorff sets. So we have that setting where we have Gromov Hausdorff convergence, and the limit is compact. Then a subsequence of the MJK converge in the intrinsic flat sense to an integral current space that's a subset. So now, whenever you had a Gromov Hausdorff sequence, as long as you assume this uniform upper bounds on the volumes, we now have a subsequence which converges to something the correct dimension. But it's a subset. It's not necessarily the whole set. And we already saw that with the sphere and the line segment. It was just the sphere, not the line segments. This was proven using Ambrosio-Kirchheim's compactness theorem and Gromov's compactness theorem together. So they have a compactness theorem for integral currents, which is just like Federer-Fleming's, which says you assume an upper bound on volume and that they're all in a compact region together. One corollary of this is that if the Gromov Hausdorff limit is lower dimensional, then the intrinsic flat limit is 0. Okay, so if it's lower dimensional, as in this picture, the intrinsic flat limit is 0. It was always called collapsing in Gromov Hausdorff theory. You call it collapsing if the volume went to 0. So now, or the dimension went down. And so we now see that this is not the setting we're in. We're in the setting where there's no collapsing. So it's also possible for things to go to 0 in the flat sense without collapsing. So here we are in Euclidean space, and now I'm just doing the weak limit or flat limit in Euclidean space of a bunch of sheets sitting in Euclidean space. And if you take a sheet and you integrate up and then you integrate back down, and the sheet gets thinner and thinner, it disappears. They cancel. The positive orientation and the negative orientation, they canceled out. So it disappeared. It went to 0, or this whole segment disappeared suddenly. So we were concerned, can this happen when we have isometric embeddings? Because that's not isometrically embedded. That plane has shortcuts between planes. So we were like, okay, maybe we can do the shortcuts. And so we created this example, which is a little hard to see. You take two sheets and you put tubes between them, little black holes between the two sheets, all over the place. So think of it as two universes with lots of black holes running between them. They're shortcuts so that the distances between these two sheets is coming close. And if you increase the number of holes and you bring them closer and closer together, these also disappear suddenly in the limit. And we were concerned this is a problem with our whole convergence. If everything disappears all the time, what's the use of it? Right? So how can you avoid something like this happening? And so what we noticed was that while this didn't happen in Euclidean space, in the setting of the Riemannian surfaces here that were canceling, the topology was going crazy. There was just more and more and more topology all over the place. So there's a topological effect. So to avoid cancellation, we started to study this topological effect. So we have two theorems that show there's no cancellation in two different settings. So the first setting is based on a theorem of Greene-Petersen, which uses Gromov. If you have a sequence of Riemannian manifolds that have a uniform linear geometric contractibility function, which I will define soon, it's a contractibility. And you assume the bond is bounded above, Greene-Petersen proved that a subsequence converges in the Gromov Hausdorff sense to a metric space, and they used Gromov's compactness theorem. What they did was they showed they could count the number of balls in this setting. So if there was a contractibility, and I'll describe this contractibility better, but it's not too many holes like in that picture, then there was convergence. In that setting, we can prove that the flat limit agrees with the Gromov Hausdorff limit in that contractibility setting. This is already on the archive, but we have it phrased in geometric measure theory language in our paper there. So one consequence of this is that we now know Greene-Petersen's limits are countably HK rectifiable, which was not known before. So we now have a certain amount of rectifiability on their limit spaces. And I had said before, Cheeger-Colding had proven rectifiability in their setting. So here's Cheeger-Colding's setting, right? So just contrast it. Cheeger-Colding had shown if you have Ricci bounded below, volume bounded below, and diameter bounded above, the subsequence converges to a countably HK rectifiable space. So they already proved that in the Ricci setting. But now we see that it's true in this other setting, which is disjoint settings. They don't agree, they're not overlapping. Ricci curvature can have many, many tiny holes. And although we don't get a new result about the countable HK rectifiability, we do show that the intrinsic flat limit agrees in that setting too. So both of these settings, the intrinsic flat and Gromov Hausdorff convergence had agreed. And Wenger, who's been mentioned a few times, so Wenger, he proved that there's no uniform geometric contractibility in this setting. He has the examples that have many, many, many little holes in the Ricci setting. So let's just do one more example before I can talk about those proofs if I have time. So the positive scalar curvature, which was the original question that Lehman had been interested in. Is it possible that in the positive scalar curvature setting, this is open, okay, one might be able to avoid cancellation somehow? So we have, and this example shows that sometimes you can't avoid cancellation. So you can construct three-dimensional manifolds with positive scalar curvature. They take a sphere, a three-sphere, with constant sectional curvature. Take a second three-sphere with constant sectional curvature. Now we bring them close by putting all these little Gromov-Lawson tubes between them. Those are like little black holes running between the two three-spheres. You make as many as you want to make the three spheres get closer and closer. The limit will cancel and be zero. So at first glance, it's like, oh great, our flat distance doesn't work for scalar curvature. However, that particular sequence of examples has many interior minimal surfaces. And it's very natural when studying scalar curvature to say, I have a manifold with no interior minimal surfaces. Just the boundary is minimal surfaces. So you would look at in this particular case, you have your two spheres with all your little holes all over them, cut them in half at all the minimal surfaces. You've got one sequence over here, that's the inside, and the other side, with the minimal surfaces of the boundaries. Say, okay, let's study this half, and see if it converges without cancellation. So that's sort of what we're leaving open. Perhaps one can prove that that sequence will never have any cancellation. Now, they can have gravity wells all over the place, so you will have things disappearing that you want to disappear. But you want to say that it doesn't disappear completely to zero. You have enough still there. Strangely, we can also, with a very slight adjustment, have a sequence that goes to multiplicity 2. So the multiplicity 2 version is you take your one sphere and your other sphere, and instead of joining them just with little Gromov-Lawson tubes, you take your little tubes and you loop them around and attach each little tube with a little extra loop, like you're crocheting them together. So it's like little twine balls all over the place. Then you reverse the orientation, so they're meeting each other with the same orientation, and it comes to multiplicity 2 in the limit. A sphere with multiplicity 2. That's kind of a weird effect. So we believe the cancellation, and also we believe the multiplicity thing does not occur if you assume there are no interior minimal surfaces. We don't mind, and we want regions to disappear like the hairs, but you don't want cancellation of two different sheets.
So
This is a vaguely stated conjecture.
What's the math statement and no interior minimal surfaces? What's the statement?
What's the
What's the
statement?
assumption? The shows are just words. I mean, what's the math statement?
The no interior minimal
Pretending I understand this other example, which is up, so I don't know what those words mean. No interior minimal surface.
No interior minimal surface means that there's no minimal surface that's a closed minimal surface of a compact Riemannian minimal surface inside the manifold. So
What's the dimension? What's the dimension thing?
we're all in 3 dimensions here. So the minimal surface is a hypersurface that's minimal. But if you picture this in 2 dimensions as spheres with tubes, then the minimal surface is a geodesic, closed geodesic, that's going around the black hole. And if it's in 3 dimensions, the minimal surface is like that event horizon thing. So it's like saying I want to stay on my side of the universe, and I don't care what's happening on the other side of the event horizon. There's one way to think of it. Anyway, that conjecture is very unmathematical. It's very vaguely stated. The conditions, but the results are not clearly stated. Okay, so what's the key observation we made? This key observation was a crucial step in showing that there was no cancellation in the case of Ricci bounded below and in the contractibility settings, the Greene-Petersen and the Cheeger-Colding settings. So the key observation we made is we looked at what happens when 2 sheets come together and cancel in Euclidean space. And what happens is, so let's just cut out a ball there that's going to disappear. You cut out the ball, and you look at the boundary of the ball. So in the first step I have just a sheet, then I look at the cutout ball, then I look at the boundary. So I expanded the boundary so you could see it better. And then I filled it in with a different minimal surface. So we noticed that whenever 2 sheets come together, the boundaries of balls could be filled in much more efficiently with this thin little thing instead of these 2 sheets that are canceling. The same effect occurs with the intrinsic flat distance. The 2 sheets coming together with the many holes between them, there's all these little annuline tubes coming through here. You make your boundary of your ball, goes around, and you fill it in. And there's this much smaller filling that's occurring. So the key observation is, when can we prevent the existence of a smaller filling? If there's no smaller filling, then it doesn't cancel. So anyone trying to prove the scalar curvature theorem should be looking for the conjecture. Should be looking for when can you make spheres in a Riemannian manifold positive scalar curvature not have a small filling. And this filling is in the sense of Gromov filling. So we can use Ambrosio-Kirchheim slicing theorem to make this rigorous. So Ambrosio-Kirchheim had a slicing theorem which goes with Federer slicing theorem. Federer slicing theorem said you have a sequence of currents and converge. You could slice them and look at level sets of an Lipschitz function against the slices. And so boundaries of spheres versus balls. A ball converges, then the boundary of the sphere converges. That's their slicing theorem. It doesn't work for every radius, but it works for almost every radius. So it's useful to us. And it's the same as Fedor-Fleming-Sisson theorem. So I think I have enough time to start talking about the actual proof of the Greene-Petersen situation. And I can define the uniform geometric contractibility better. So here was Greene-Petersen's theorem statement again, their theorem. They assume a uniform geometric contractibility function. So what is that? That means you have a ball, any ball, in your manifold of any radius r, and it will contract inside a ball of radius rho of r. So the function is rho of r. That's how far out you have to go to contract your ball. They assume that there's a uniform rho, and they assume that the volume is uniformly bounded below, and they're able to show that the volume they assume the volume is uniformly bounded above. They're able to prove the volume is then uniformly bounded below. So if these balls have contracting in a uniform rho for all the sequence mj have the same rho, then the volume is bounded below for all balls, and a subsequence converges in the Gromov Hausdorff sense. Yes?
You don't contract just for all R, don't you want just for little r?
It doesn't matter. Because I just need a uniform contractibility function rho. So I could just say, yes, right. I could say the domain of the uniform contractibility function is 0 to r naught, as long as r naught is the same for the whole sequence. As long as it's the same, it doesn't have to be contractible space. But they all have to have contractibility. The domain of this contractibility function has to be the same for all. So we can't have it smaller and smaller for the sequence. So in our setting, we're able to prove that if rho is linear, okay, so theirs is in general, any rho, you get this Gromov Hausdorff. We show that if rho is a linear function, then the flat limit and the Gromov Hausdorff limit agree. So if it's a linear function, so proportionality going on here, then they agree, and Scholl and my co-author Stefan have proven that if you don't assume linearity, the limit space is not necessarily countably HK rectifiable. So there's no hope. Okay, so linear is a necessary condition. So I'm going to draw the picture so you can see this. Here's a picture of linear contractibility. This ball here, which is near a cone tip, this ball contracts within a radius of twice its radius. You see that? If you go twice the radius, you can get over the tip. So that ball, even though it wrapped around, it's not contractible in itself. But if you double the radius, it can pull over the tip and contract. That little ball over there, again, double the radius, you can pull over the tip. So the conical tips are linearly contractible. And this example of a sequence that we said flat converge to something with a conical tip, these are uniformly linearly contractible. Okay, this one's not linearly contractible. This sequence, okay, the first ball, double the radius gets you over the tip. The second ball, you need to quadruple the radius to get over the tip. The next ball, you need 10 times the radius to get over the tip. So it's not a linear contractibility function for that sequence. There is a uniform contractibility function for the sequence, but it's not linear. And in our case, we don't include the tip. The tip didn't have positive, remember we need positive density for every point in our limit space. So we're not including the tip in our space. And here we see a sequence. This is actually linear contractible for balls that avoid that tip, but sequences of balls approaching the tip do not have a linear contractibility. So we don't include the tip. This is a very simplified situation. The pictures could be much worse. So here's a much worse picture. Here's Perelman's example of a sequence of non-collapsing four-dimensional manifolds with non-negative Ricci curvature and the topologies going to infinity. So what they are is, they are very high curvature on this edge. So there are two four-dimensional disks that meet with very high positive sectional curvature on the edge. Then he glues in holes all over the place with the positive Ricci. So I drew those holes like little black holes there, little black dots. And he can, as he makes the edge sharper and sharper, he can glue more holes on. And the Gromov Hausdorff limit is, in fact, this two disc things meeting with a sharp edge. But it is actually a conical edge, not a cusping edge. And the intrinsic flat limit in this example agrees with the Gromov Hausdorff limit. Remember, we proved all non-negative Ricci with the volume bounded below. They agree. So any proof we do that involves contractibility cannot just be immediately applied here. That's a reminder of the theorem about the Ricci. Okay, so how do you start the proofs of the contractibility and Ricci theorem? So the beginning of the proofs is the same for both. In both settings, we take a sequence of manifolds which are converging in the Gromov Hausdorff sense, and they have volume bounded above. And we want to show that they converge in the flat sense, and that the flat limit is the whole space, not just the subset. So by Gromov, with his contractibility theorem, which is in his groups of polynomial growth paper, not his metric structure paper, there's a compact metric space Z and isometric embeddings of all these into a common space Z. And they Hausdorff converge in a common space Z. This is a serious theorem. It's not just a consequence of compactness. It's like he actually puts them all into a common space. That's compact. And then shows it has a limit. Ambrosio-Kirchheim had extended Federer-Clemens result, which says that if you have a sequence of integral currents with a uniform upper bound on their mass, and they're all in a compact set, then a subsequence converges. So we can apply that theorem, and we get a subsequence which converges to an integral current, and then we choose this to be our integral. This is our flat limit now. This limit integral current, which is actually sitting inside the Gromov Hausdorff limit, physically sitting inside Gromov Hausdorff limit, inside this huge compact metric space Z. They all fit in together. So it's pretty compact. And we know that if you have a point Y in your limit space, in your Gromov Hausdorff limit, see Y is our Gromov Hausdorff limit, and X is going to be our X is the intrinsic flat limit. Y is the bigger one. That's the Gromov Hausdorff. We have a sequence of Y's always converging to the Gromov Hausdorff limit. And so we can study balls around these. So now we're saying, okay, I'm taking balls inside my sequence, and they're converging to a ball in the limit space. So we have balls. This notation is a geometric measure theory notation. You take the current and you restrict it to the ball. So it says integration over ball. Integration over balls converges to integration over a limit ball. So we need to show, we want to show Y is actually in this set with the positive density. That's how we show it's in the intrinsic flat limit. We want to show it's in the set with positive density. We don't want it to be a cusp point. We want it to be a cone point or even a nicer point. So we want to show that our Y is not a cusp point. We want to show this mass is controlled. We don't want any cuspy points. The problem is, even if we can control the mass of the sequence of balls, even if we control the volumes or masses of the sequence of balls here, it could drop suddenly in the limit to 0, which is what happens in those pictures that we had. So I think I put the pictures back up again. Here. In this picture, the mass of the balls dropped. It disappeared because the two sheets canceled. So you have a sequence of balls, the two sheets cancel, and disappear. So how can we show the mass of a limit is bounded below if the mass of the sequence could suddenly drop to it? And the same thing can happen with intrinsic flat. So this is where I use the slicing. We use the slicing theorem, which I mentioned before we were going to use. Instead of studying the balls themselves, we study the spheres. And we say, okay, when can we make sure the spheres converge? Well, the spheres weakly converge almost everywhere, almost every R by Ambrosio-Kirchheim slicing. And then we apply a paper of my co-author which says that the filling volumes, this is the Gromov filling volumes, the filling volumes converge. It's not like the mass. The mass could drop in the limit. It's only semi-continuous. The filling volumes actually converge. So filling volumes are basically like how can you fill it in, but in an intrinsic sense. So that's it. We have to bound the filling volumes, and the key step is Greene-Petersen actually already bounded the filling volumes. That's how they did their theorem. They had bounded filling volumes using Gromov-Hausdorff constructions and his inequalities. Now, actually, we didn't use Greene-Petersen, but when we thought of this, we were like, oh, wow, we reduced it to Greene-Petersen. But here, we actually used Lang-Schlickenmeyer's result because we prove a more general theorem than the Riemannian one. And they have something that applies to non-manifolds. So that's the basic key step. And we are done with the green when we have the contractibility. Because Greene-Petersen showed contractibility implies filling as control. And once we have filling control, we can control our ones. So I think I'll stop here. Thank you very much.
These spaces compute the algebraic topology correctly.
On these spaces, can you correctly compute algebraic topology?
You could have inside manifolds, inside cycles.
I am not sure. There's that problem because you have these disjoint charts, and then they just meet. They might miss a set of measure 0, and that could affect the topology. So, yeah, it's not that great for that.
You were talking about the boundary before. You had a notion of boundary.
We have a notion of boundary. So there's a possibility someone could develop this, but it doesn't follow immediately. Yeah. Actually, to be honest, rectifiable spaces have been studied a lot by Kirchheim, so I would ask him before, maybe they're already looking into it.
What was the author's motivation for the question he posed at the beginning of the talk? Was that the coordinate?
He wants, you probably know better than me. He wants to, okay, if you think of the world as all really being partial differential equations, which I have somewhat of a biased perspective, okay, then you need a way to measure the distance between solutions to your partial differential equations. If you think of Riemannian manifolds as solutions to partial differential equations, you should be able to measure stability and things like that. There's no stability. The Gromov Hausdorff has been useful for some kinds of stability and been very useful when you add the Ricci curvature condition. Amazing amount of stability, almost rigidity, it's called, theorems, with Gromov Hausdorff when you add Ricci. But Ricci is a very strong extra condition to add. So you want something weaker. Now you guys, go ahead. Use it. We're scalar curvature experts. Anyone? Yes.
In the beginning, you were saying there were preprints or you also have these bound on.
Not mine. My co-author has a compact theorem.
I was interested in the bound area and.
It's a bound.
Boundary.
Yeah, you assume it's the volume, the bound on the volume, and bound on the volume of the boundary. Uniform. That's it. And diameter. Sorry. Yes, and it's been on, okay. He proved it for geometric measure theory set. That paper is on the archive. But it translates immediately to this. Like it immediately applies here. So because it was a very important geometric measure theory result, it has its own paper. And then, and we posted also the agreement with the Ricci and the agreement with contractibility. That's also already on the archive, but written in geometric measure theory language. And right now we're finishing up a very, very long preprint, which explains all this in terms of Riemannian geometry and explains how those apply, but doesn't redo the geometric measure theory.
Is it true that if you start with Riemannian manifolds, then it is
It's an integral current space, which isn't defined in his paper, but it's defined in ours. Integral current space is what we say here. So I'll put these transparencies up on the webpage right away, and that is the definition of integral time space. So it's a space with liquid starts and orientation, and it has boundaries.